Hello, friend. Welcome back. Or if this is the first time you've found your way here, welcome. Close your eyes for just a moment. Imagine you're standing in a dark room, perfectly still, perfectly quiet, and you flip on a light switch. The room fills with light. Simple. Predictable. You know exactly what will happen before you do it. Now imagine that the moment you tried to watch that light travel through the air, it changed. It rearranged itself. It behaved differently just because you were paying attention. What if I told you that isn't imagination? What if I told you that is exactly what the universe does every single second of every single day right now? All around you in the air, between your fingers and the atoms inside your bones. Welcome to the world where reality isn't a fixed thing. It's a suggestion. And the deeper scientists look the stranger, everything got. Before we drift into the beautiful strangeness of it all, if these quiet journeys into science bring you some peace at the end of a long day, you might like to stay a while. You can gently tap the like button. It helps more people find this little corner of calm. Subscribe if you'd like more stories told softly, and ring the bell not for noise, but so the next quiet night can find you again. Now, let's drift. Tonight we are going to travel together through 9 doorways into the quantum world. A world that is not strange because scientists made it strange. A world that is strange because that is simply what it is. Strange before we found it. Strange after we understood it. Strange in ways that physicists who spent decades studying it still whisper about when the room gets quiet. And the story of how we got here, how humanity stumbled into this hidden layer of reality, begins not with a genius in a laboratory, but with a crisis. A deep, unsettling feeling that something was wrong, that the map we had drawn of the universe was beautiful and elegant and almost certainly incomplete. Let's go back, all the way back to the late 1800s. For nearly 2 centuries before the quantum era, science was riding a wave of extraordinary confidence. And honestly, the confidence was earned. In 1687, Isaac Newton published his Principia Mathematica, and with it, he handed humanity something that felt like the master key to the universe. His laws of motion and gravity could predict the path of a cannonball, the orbit of the moon, the swing of a pendulum. Everything moved according to rules. Everything was in principle calculable. Give me the position and speed of every particle in the universe, the French mathematician Pierre-Simon Laplace declared in 1814. And I will give you the entire future. That was the dream. A clockwork universe. Order deterministic knowable. And for centuries it held. Beautifully, predictably. James Clerk Maxwell unified electricity and magnetism in the 1860s. Thermodynamics gave scientists a precise language for heat and energy. Chemistry was being mapped atom by atom. There was a famous story, though. Its exact origin is debated, that a physicist in the 1890s advised a young student not to go into physics because he said all the important discoveries had already been made. All that was left was to measure things more precisely. All the important discoveries had already been made. Can you feel the weight of that sentence? Can you feel the irony sitting inside it, waiting? Because then came the light, not figuratively, literally. Light. In 1887, 2 American scientists, Albert Michelson and Edward Morley, conducted an experiment in Cleveland, Ohio, that was supposed to confirm something about the way light travels through space. At the time, scientists believed that light-like sound needed a medium to travel through. They called it the luminiferous ether, a substance that supposedly filled all of space, invisible, undetectable, but absolutely necessary for light waves to move. The experiment was elegant. They split a beam of light in 2, sent the beams in perpendicular directions, and expected to see a tiny difference in travel time based on Earth's motion through the ether. They found nothing. No difference. No ether. The experiment that was supposed to confirm the old model instead cracked it, quietly, without fanfare. A small result on paper that took years for its full implication to sink in. Then, in 1900, a German physicist named Max Planck was trying to solve what scientists called the ultraviolet catastrophe. Classical physics predicted that a glowing hot object like a heated piece of metal should radiate infinite energy at high frequencies. Obviously, that didn't happen in reality. Something was wrong with the equations. Planck fixed the math, but the fix required something uncomfortable. He had to assume that energy doesn't flow in a continuous stream. It comes in discrete little packets. He called them quanta from the Latin word for how much. Planck himself thought it was just a mathematical trick, a convenient fiction to make the numbers work. He didn't truly believe energy was actually packaged in little bundles. He thought reality was still smooth, still continuous, still classical. He was wrong about his own discovery. 5 years later, in 1905, Albert Einstein took Planck's idea seriously. Einstein was working at the Swiss Patent Office in Bern, 26 years old, spending his lunch breaks thinking about light. He looked at something called the photoelectric effect, the fact that when light hits certain metals, it knocks electrons loose. And he noticed something strange. If you increase the brightness of the light, more energy, you might expect the more energetic electrons to come flying off. But that's not what happened. Change the frequency of the light and the electron energy changes. Change only the brightness and the electrons barely change at all. Classical physics couldn't explain this. Waves of energy shouldn't behave this way. Einstein proposed that light wasn't just a wave. It was made of discrete particles, little packets of energy, what we now call photons. Each photon carries a fixed amount of energy based on its frequency, and when it hits an electron, it either has enough energy to knock it free or it doesn't. More photons don't help if each one is too weak. Light was a particle, and also a wave, both at once, somehow. Neither term quite capturing the reality. Einstein published 4 remarkable papers that year. This was one of them. It would eventually win him the Nobel Prize in 1921, not for his famous work on relativity, but for the photoelectric effect, for the photon, for cracking open the door to quantum theory. And once that door opened, it couldn't be closed. Now here is something worth pausing on, because there is a common misunderstanding about this moment in history that I want to gently correct. Many people think that quantum mechanics came along and replaced Newtonian physics, proved it wrong, threw it in the garbage. That's not quite right. Newton's laws still work, beautifully. They still predict the trajectory of a baseball, the orbit of satellites, the path of a rocket to Mars. They just don't work at very small scales, at the level of atoms and subatomic particles, where quantum effects become dominant. Think of it this way. Imagine you were drawing a map of a city. At the scale of streets and neighborhoods, the map is accurate. But if you zoom in to the level of individual bricks in a wall, the flat map no longer captures the texture and depth of what's really there. You need a different tool, a different language. Classical physics is the city map. Quantum mechanics is the electron microscope. They don't contradict each other so much as they describe different layers of the same reality. It's just that the deeper layer turned out to be far weirder than anyone had imagined. By the early 1920s, a new generation of physicists was gathering. Young, brilliant, almost recklessly imaginative. Niels Bohr in Copenhagen, Werner Heisenberg, who was so mathematically gifted that his university thesis committee almost failed him because he couldn't explain how microscopes worked. Erwin Schrödinger in Vienna, Paul Dirac in Cambridge, so quiet and precise that his colleagues joked that his unit of speech was 1 sentence per hour. These men and a handful of extraordinary women like Lisa Meitner, who contributed ideas that were rarely given their full credit, were building a new physics, not fixing the old one, building something genuinely new. And the things they discovered were not just scientifically shocking, they were philosophically destabilizing. At the heart of the new quantum theory was an idea so strange that even the people who proposed it argued about it for the rest of their lives. An idea that says the universe at its most fundamental level does not have a definite state until it is observed, until something interacts with it, until the universe in some sense is asked a question. Before the question, there is only possibility, a shimmering cloud of probabilities. Multiple realities existing simultaneously overlapping, undecided. And when the question is asked when an electron is detected, when a photon is measured, the probabilities collapse. One outcome becomes real, the others vanish. Or do they? Think about what that means for a moment. The chair you're sitting in right now, the walls of your room, the quiet air. They feel solid, definite, unambiguous. But they are made of atoms. And atoms are made of subatomic particles. And those subatomic particles, when you look closely enough, do not behave like tiny billiard balls with fixed positions and precise velocities. They behave like waves of possibility, smeared across space, uncertain, probabilistic. The solidity. You feel the hardness of the floor, the weight of your body that is an emergent property, something that arises when you have trillions upon trillions of uncertain particles all interacting together in ways that, at the macroscopic scale, average out to something that feels fixed. Solid is an experience, not an absolute truth. Here is a question that scientists and philosophers have been wrestling with for a century. If the act of observation changes what is being observed, if the measurement itself participates in creating the outcome, then what does that tell us about the nature of reality? Is there a universe out there fully defined, fully real, waiting to be discovered? Or does reality in some deep sense only crystallize when something is there to witness it? Niels Bohr, who was one of the founding architects of quantum theory, believed there was no point in asking what an electron really is when no one is looking. The question itself was meaningless, he said. Reality for Bohr was inseparable from the act of measurement. Einstein hated this. He famously objected in a letter, essentially asking, "Do you really believe the moon doesn't exist when no one is looking at it?" Bohr's response at its core was, "The moon is a very large collection of particles. And at that scale, quantum uncertainty averages out to something that behaves classically. But for a single electron, that's a different question entirely." This argument between Bohr and Einstein, two giants of 20th century science, genuine friends who respected each other deeply and disagreed on this point for the rest of their lives, is one of the great intellectual dramas of modern science. And what makes it so resonant, so deeply human, is that neither of them had the luxury of a clean answer. The experiments weren't precise enough yet. The theory was still being built. They were standing at the edge of a new world arguing about its nature, with only partial maps and imperfect instruments. Think about what that feels like. To know that something enormous is there, to have the mathematics pointing toward it, the experiments confirming the weirdness, the data piling up, but to not yet fully grasp what it means. That is where the story of quantum mechanics lives. Not just in equations on a blackboard, but in the human experience of confronting a universe that refuses to be simple. Heisenberg once wrote that the universe doesn't consist of matter, but of possibilities. That the real is not the thing itself, but the potentiality for the thing. He wrote this not as poetry, but as a statement of fact, as the conclusion he had arrived at after years of staring at equations that would not resolve into comfortable certainties. Possibility. Not the thing, the cloud of what might be. There is something strangely peaceful about that if you let yourself sit with it. We spend so much of our waking lives trying to control outcomes, to fix the future in place, to know, to be certain. And here at the foundation of everything in the smallest bones of reality is this radical uncertainty, this unresolvable openness, not as a failure of knowledge, but as a fundamental feature of the universe itself. The universe does not decide in advance, neither perhaps should we. As we begin to drift deeper into the quantum world tonight, the first real experiment we're going to visit is one of the simplest in all of physics. So simple it involves only a beam of light, two tiny slits in a piece of cardboard, and a screen. And what it shows is so strange, so genuinely profoundly strange, that Richard Feynman, one of the greatest physicists of the 20th century, said it contained the only mystery of quantum mechanics. That if you truly understood this one experiment, you understood everything that is difficult and beautiful and baffling about the quantum world. He called it a phenomenon that is impossible to explain in any classical way, and which has in it the heart of quantum mechanics. The double-slit experiment. It's waiting just ahead, and what it reveals about the nature of light and matter will quietly change the way you see everything you look at tonight. That experiment Richard Feynman called the only mystery in quantum mechanics, the one he said contained the entire heart of the quantum world, begins not in a high-tech laboratory filled with humming machines and at glowing screens. It begins in a room that is almost embarrassingly simple, a light source, a barrier with two narrow slits, and a screen on the other side to catch whatever comes through. That's it. That is the setup that broke classical physics and hasn't finished breaking minds ever since. The double-slit experiment is not new. The first version was performed in 1801 by a British polymath named Thomas Young. And the reason he ran it, the question he was trying to answer, tells us everything about why what happened next was so unexpected. In 1801, the scientific world was divided. On one side stood the legacy of Isaac Newton, who believed light was made of tiny particles, what he called corpuscles. On the other side were scientists like the Dutch physicist Christian Huygens, who argued light behaved like a wave rippling outward like the surface of water when you drop a stone. Thomas Young believed Huygens was right, and he designed a devastatingly elegant experiment to prove it. He let light pass through a single narrow slit first, which spread the beam like water flowing through a gap in a wall. Then he let that spread beam hit a second barrier with two slits side by side. On the far side, he watched what appeared on the screen. If light were particles like tiny bullets fired through two holes, you'd expect to see two bright bands on the screen, one behind each slit. The light particles go through hole 1, they land in one spot. The light particles go through hole 2, they land in another spot. Simple. But that is not what Young saw. Instead, the screen filled with a series of alternating bright and dark bands. Not two bands, many bands, spreading outward in a pattern that physicists call an interference pattern. This only happens with waves. Think of two stones dropped into still water at the same time close together. Each stone sends out ripples in expanding circles. Where two ripple crests meet, the water rises higher, the waves add together. Where a crest meets a trough, they cancel each other out, the water goes flat. The result is a complex, beautiful pattern of high and low points spreading across the surface. Young's light was doing exactly this. The light waves spreading from slit 1 and slit 2 were interfering with each other, adding together in some places, to make bright bands canceling in others, to make dark bands. Light, Young concluded, was a wave, not a particle. Newton, it seemed, had been wrong. For about a century that answer held. Light is a wave. Problem solved. Then Einstein came along in 1905 with the photoelectric effect, which we touched on in the first part of our journey, and showed that light also behaves as a particle, as photons, discrete packets of energy. And suddenly the neat answer unraveled again. So scientists asked the obvious next question. If light is both a wave and a particle, what happens if you run the double-slit experiment with a single photon at a time? Just one. One tiny quantum of light fired at the barrier. Where does it land? If it's a particle, it should go through one slit or the other, and over time, as you fire thousands of individual photons, you should see two bands building up on the screen. What they actually observed quietly unsettled everyone in the room. Fire enough individual photons one at a time, each one traveling alone with no other photon nearby to interfere with, and the interference pattern builds up anyway. Slowly, one dot at a time, the same ripple bands appear on the screen. Each individual photon traveling alone seems to interfere with itself, as if it somehow passes through both slits, at once split across two paths simultaneously, and the two paths interfere with each other on the way to the screen. How does a single particle pass through two openings at the same time? The answer that quantum mechanics gives is deeply unsettling. The photon before it is detected does not have a definite path. It exists as a wave of probability spread out unresolved genuinely in multiple places at once. It goes through both slits, not because we don't know which slit it took, but because before measurement, there is no which slit. There is only the probability wave. And then comes the moment that makes this experiment truly extraordinary. Scientists wondered, what if we simply watch? What if we place a detector right at the slits? A tiny camera, a particle sensor, just to find out which slit the photon actually goes through. They did it. They set up detectors at both slits. And the moment they turned the detectors on, the interference pattern vanished. With the detectors running, the photons started landing in just two bands, exactly what you'd expect from particles going through one slit or the other. The wave behavior disappeared. The quantum weirdness retreated. Turn the detectors off again. The interference pattern returns. Turn them on. It disappears. Physicists have repeated this in hundreds of variations over the decades with increasingly sophisticated equipment, and the result is always the same. The act of measuring of gathering information about which path the particle takes fundamentally changes the behavior of the particle. It is not that the detector disturbs the photon physically. It is not a question of bumping it or pushing it off course. The information itself, the mere fact that the universe now contains knowledge of which path was taken, is enough to collapse the quantum behavior and produce a classical result. The universe, it seems, keeps score. And here is where I want to pause because there is a very common misunderstanding about this experiment that I want to address carefully. Many people hear this result and jump to a conclusion that even some popular science books have unfortunately encouraged. They say consciousness causes the collapse, that human observation, the awareness of a thinking mind, is what changes the quantum outcome, that we as conscious beings are somehow participating in creating reality at a fundamental level. This is a misreading, an understandable one, but an important one to correct. The observation in quantum mechanics does not require a conscious observer. It does not need a human eye or a human brain. What collapses the quantum wave function is not awareness. It is physical interaction. Any physical process that records which path information. A photon bouncing off the particle, an electron being deflected, a detector registering a signal produces the same effect. You could put a camera no one ever looks at in front of the slits, and as long as that camera records the data, even if the recording is never played back, even if it sits on a hard drive in a sealed room, the interference pattern still disappears. It is not consciousness, it is information, the physical encoding of which path knowledge in the state of the universe. This distinction matters enormously because the version with consciousness, while poetic, suggests something mystical and untestable. The version with information points towards something precise and profound, that the physical storage of information is connected in some fundamental way to what we call reality. A harder thing to grasp, perhaps, but a more honest one. Now, what makes this even more extraordinary is that the experiment has been run not just with photons, particles of light, but with electrons, with neutrons, with entire atoms. And in 1999, with molecules of carbon-60 called buckyballs, each containing 60 carbon atoms, a structure you could almost see in a decent microscope. The interference pattern appeared for all of them. Wave-particle duality. This strange hybrid nature is not something unique to light. It appears to be a fundamental feature of all matter at small enough scales. Your own hand is made of electrons and protons and neutrons, and each of those particles carries within it this same mysterious duality. The reason your hand feels solid and not wave-like is because at the scale of hands, the quantum effects average out into classical behavior, the same kind of decoherence we'll explore later in our journey tonight. But the waves are there. The duality is there, buried inside every object you have ever touched. And perhaps the most philosophically stunning extension of the double-slit experiment is a version called the quantum eraser, first proposed in 1982 by physicists Marlon Scully and Kai Druhl, and experimentally confirmed in the years that followed. In the quantum eraser, researchers set up the detectors to record which path information, killing the interference pattern as expected. But then after the photon has already been detected on the screen, they erase the which path information. They destroy the record, and the interference pattern in the correlated data reappears. Think about the implication of that for a moment. The photon has already hit the screen. The outcome has already occurred. And yet, erasing information about the path information recorded after the fact changes the statistical pattern of outcomes that were already measured. The timeline of cause and effect seems to bend. This does not mean the future is changing the past. In a literal sense, there are careful technical reasons why the quantum eraser cannot be used to send messages backward in time. But it does suggest something genuinely strange about the relationship between information time and the physical world. Niels Bohr once said that anyone who is not shocked by quantum mechanics has not understood it. He said this not as a challenge, but as a warning, as an honest report from someone who spent his life inside the mathematics and still found it mysterious. The double-slit experiment is where that shock is born, where the clean mechanical story of reality first begins to tremble, a particle that is also a wave, a path that is both paths until it is measured, an outcome that seems to depend on what information exists in the universe. And what is remarkable, what should perhaps fill you with a kind of quiet wonder as you settle into the night, is that this experiment has never been explained away. No one has found a hidden mechanism that resolves the paradox. No one has shown that the particle secretly chose one path all along and we just didn't know it. As far as we can tell, the duality is real, the superposition is real, the role of measurement is real. The universe held the answer in two places at once until we asked. And all of this, every strange, shimmering implication of the double-slit points directly toward a deeper principle. A principle that doesn't just apply to photons traveling through slits, but to every particle in existence, to the atom inside your cell, to the electron inside your thought. The principle that a quantum object does not have a single definite state at all until something forces it to choose. That principle has a name, and it is perhaps the strangest idea in all of science. It's called superposition. And the story of how scientists discovered it and what it truly means, including the one thought experiment that became the most famous in the history of physics, is exactly where we're going next. Superposition. The idea that a particle, an electron, a photon, an atom, does not have a single definite state until something forces it to have one. That before measurement, before interaction, it exists in a kind of suspended in between. Not here, not there. Not spinning up, not spinning down. Both and neither all at once. It is the strangest sentence in all of physics. And it is true. To understand superposition, really understand it. Not just recite the word, we need to go back to the mathematics. Not deep into the equations themselves, but into what the equations were telling the people who wrote them. In 1926, the Austrian physicist Erwin Schrödinger published what became one of the most important equations in the history of science. It describes the behavior of quantum systems over time, how the probability wave of a particle evolves, spreads, shifts, and moves. It is called the Schrödinger equation, and it is by the standards of physics elegant and precise. What the equation describes is not a particle with a position. It describes a wave function, a mathematical object, that encodes the probability of finding a particle in any given state when you measure it. Before measurement, the wave function spreads across multiple states simultaneously. A particle might have a 30% chance of being found here, a 45% chance of being found there, and a 25% chance somewhere else entirely. All at once, all real, all present in the mathematics. This is superposition. Not a lack of knowledge about which state the particle is in, not an approximation, a shortcut, or a modeling trick. According to quantum mechanics, the particle is genuinely physically in all those states simultaneously until measurement. And that word, until, carries everything. Schrödinger himself wrestled deeply with what his own equation was saying. He was a brilliant, restless man, fluent in multiple languages, deeply interested in philosophy, famously complicated in his personal life, and genuinely troubled by the implications of the theory he had helped build. He did not believe that the wave function represented a physical reality. He thought it was a mathematical tool, a calculation device, not a description of something that truly existed. By 1935, after years of debate with Niels Bohr and others, Schrödinger's frustration reached a breaking point. He decided to construct what he called a ridiculous case, an extreme example designed to show just how absurd the full implications of superposition would be if you took the mathematics seriously at the macroscopic scale. He imagined a sealed steel chamber. Inside the chamber, a living cat, a small amount of radioactive material, a Geiger counter, a tiny hammer, and a glass vial of poison. The radioactive material has exactly a 50% chance of decaying within 1 hour. If it decays, the Geiger counter detects it, triggering a mechanism that drops the hammer, shattering the vial, releasing the poison, killing the cat. After 1 hour without opening the box, is the cat alive or dead? Classical intuition says of course the cat is either alive or dead. We just don't know which. Our ignorance of the outcome doesn't change the reality of it. But strict quantum mechanics applied literally would say something different. The radioactive atom is in a superposition of decayed and not decayed. And if the fate of the cat is entangled with the state of the atom, then the cat itself, according to the unmodified wave function, is in a superposition of alive and dead until someone opens the box and observes it. The wave function extended to the macroscopic world produces a cat that is simultaneously living and dead. Schrödinger presented this not as a real phenomenon, but as a reductio ad absurdum, a logical proof, by showing the conclusion is ridiculous. He was saying, your theory produces this nonsense, therefore something must be wrong with how we are applying it. Here is the remarkable historical irony. He wrote the cat thought experiment to attack the Copenhagen interpretation of quantum mechanics, the view held by Bohr and his colleagues, and argue that quantum theory needed to be completed or fixed. Decades later, Schrödinger's cat became the most famous illustration of quantum superposition in history. Textbooks around the world use it to teach the very concept he was arguing against. Science popularizers put it on t-shirts and coffee mugs. The man who invented the analogy to discredit an idea became the unwitting mascot for that idea. The universe has a quiet sense of humor. Now here is where a common misunderstanding needs to be addressed, because it matters enormously for understanding what superposition actually means. Many people hear about the cat and think, well, obviously the cat is either alive or dead. We just don't know which until we look. This is called epistemic uncertainty, uncertainty about what we know. And it is completely different from ontic uncertainty, which is uncertainty about what actually is. Quantum superposition is not epistemic. It is not saying the cat is alive or dead, but we don't know. It is saying something far stranger, that in the quantum description of the system, there is no fact of the matter yet. The question, is the cat alive, does not have an answer before the box is opened. The mathematical evidence for this is not just philosophical. It comes from experiments involving a phenomenon called quantum interference, which we explored in the double-slit, where the different states of a superposition interfere with each other in measurable ways that would be impossible if the particle had secretly chosen one definite state all along. If the particle had a hidden definite state, the interference pattern wouldn't appear. The fact that it does appear reliably in experiment after experiment is direct physical evidence that the superposition, the genuine coexistence of multiple states, was real before measurement. This was not resolved by argument or thought experiment. It was resolved by data. Consider an electron. An electron has a property called spin, not like a top physically spinning, but an intrinsic quantum property that can be measured as either up or down along any axis you choose to measure. Before you measure it, the electron is not secretly spin up or secretly spin down. It is in a superposition of both. You can prepare electrons in a specific superposition and state, say an equal mix of up and down, and then measure them. Half the time you get up, half the time you get down. But here's the key. If you then run these electrons through an interference device before measuring them, they interfere with each other based on both components of the superposition, producing results that prove both states were genuinely present simultaneously. Destroy the superposition force the electron to choose before the interference device, and the interference vanishes. The quantum character of the electron is not a story we tell. It is a physical property with measurable consequences. And here is where the implications start to become almost cosmic in scale. In 1957, a young physicist at Princeton University named Hugh Everett III proposed a radical solution to the measurement problem, the question of what happens to the wave function when a measurement is made. The standard Copenhagen interpretation said the wave function collapses, that one outcome becomes real and the rest disappear. But Everett found this unsatisfying. Collapse wasn't described by the Schrödinger equation. It was just declared to happen. What if Everett asked the wave function never collapses? What if all the outcomes happen and the universe itself branches into separate non-communicating copies, each one containing a different outcome? In one branch, the radioactive atom decays, the cat dies. The observer opens the box and finds a dead cat. In another branch, the atom does not decay. The cat is alive. The observer finds a living cat. Both outcomes are real. Both observers are real. The universe has quietly split in two. This is the many worlds interpretation of quantum mechanics. And while it sounds like science fiction, it is mathematically rigorous. It requires no additional rules, no collapse mechanism. It simply takes the Schrödinger equation at face value and asks, what if it is always true? Everett's idea was largely dismissed in his lifetime. He left physics, went to work in defense research, and died in 1982, largely unrecognized. But in the decades after his death, as physicists grappled more seriously with quantum foundations, the many worlds interpretation gained significant traction. Today, it has serious distinguished advocates not as confirmed truth, but as one of the most mathematically coherent frameworks for understanding what quantum mechanics is actually describing. Have you ever made a decision, a fork in the road, a moment where either choice seemed equally possible and wondered afterward what would have happened if you'd gone the other way? Many worlds offers a strange kind of comfort. In some interpretations, both paths are real. Both yous are living their story. The universe did not choose between them. It kept both. Whether or not that is true in any physical sense, there is something deeply human about the image, the universe that holds its breath. That does not commit. That keeps all the possibilities alive until the last possible moment. Superposition is nature's version of that hesitation. Now there is an important counterpoint worth sitting with. Not everyone accepts many worlds or even the idea that superposition is physically real in the way the mathematics describes. There are physicists, thoughtful, serious ones, who hold what's called an instrumental or pragmatist view. Quantum mechanics is a tool for predicting measurement outcomes, not a picture of what reality is really like. The wave function on this view is not a physical thing in the world. It is a representation of our knowledge, our expectations, our predictive power. This debate between the realists and the instrumentalists, between those who believe quantum mechanics describes reality and those who believe it describes our knowledge of reality, is one of the oldest unresolved arguments in the philosophy of physics. It has been running in various forms since the 1920s, and it is not settled. But here is what is remarkable about this debate. It is not a debate about whether the mathematics works. The mathematics work spectacularly. Quantum mechanics is the most precisely tested theory in the history of science. Some of its predictions have been confirmed to an accuracy of 1 part in a trillion. The debate is purely about what the mathematics means, what it is pointing to, what kind of universe it is describing, and perhaps that is the most human thing about quantum mechanics. The data is clear. The predictions are exact. And we are still arguing 100 years later about what it all means. What does superposition tell us? That the universe is genuinely undecided at its most fundamental level, that nature holds multiple truths simultaneously, not as confusion, not as incompleteness, but as a feature, as a way of being. And now, having understood that particles can exist in superposition, that they genuinely occupy multiple states at once, a natural question arises. What happens when the universe is forced to choose? When the superposition ends, when observation or measurement or simply contact with the world collapses all that shimmering possibility into a single definite outcome. That moment, the instant reality is born from probability, is one of the deepest puzzles in all of science. And it comes with a principle so precise and so deeply counterintuitive that even Albert Einstein spent years trying to find a way around it. A principle that says, the more certainly you know one thing about a particle, the less certainly you can ever know another, not because of imperfect instruments, not because the experiment wasn't careful enough, but because the universe itself has built uncertainty into its foundation. That principle has a name. Werner Heisenberg discovered it in 1927. And what it reveals about the act of observation, about the relationship between the knower and the known, is exactly where we are going now. There is a moment quiet, almost invisible, that happens every time you look at something. Your eyes receive light. Your brain processes the signal. You see. Simple, automatic, unremarkable. You are the observer. The thing you are looking at is separate from you, passive, unchanged by your gaze. That is how we experience the world at human scale. And for most of history, that assumption that observation is a neutral act, that the observer and the observed are independent, seems so obviously true that no one thought to question it. Then Werner Heisenberg sat alone in a small apartment on the island of Helgoland in 1925, recovering from a bout of hay fever, far from the academic world, with nothing to do but think. And what he thought about for days alone by the sea quietly dismantled that assumption forever. Heisenberg was 23 years old. He had been wrestling with a problem that had been bothering the founders of quantum theory for years. The models they had built to describe atomic behavior were producing correct predictions, but no one really understood why. The mathematics worked, but it seemed to require that electrons jump between energy levels in atoms without ever occupying the space in between, without any continuous path, without any smooth transition. Just here, then there, with nothing in between. Heisenberg decided to try something radical. He decided to strip away all the unobservable assumptions, things like the position or trajectory of an electron inside an atom, which no one could actually measure, and build a theory based only on what could in principle be directly observed. The frequencies and intensities of the light emitted by atoms, measurable things, real things. What he produced was not an equation, but a new kind of mathematics. A framework where the quantities representing physical properties behaved in a strange way when multiplied together. Unlike ordinary numbers where the order of multiplication doesn't matter, 3 times 5 is the same as 5 times 3. Heisenberg's quantum quantities gave different results depending on the order. Position times momentum was not the same as momentum times position. They differed by a small but specific amount. He didn't fully understand what he had found. He wrote in his autobiography that when he first saw the results, he was almost frightened. The mathematics seemed to be working. The physical content was not yet clear to him, and he spent the rest of that night walking along the coast of the island, watching the sunrise over the sea. When he returned to Göttingen and showed his work to his mentor, Max Born. Born recognized what the strange multiplication behavior was. It was matrix algebra, a branch of mathematics that had been developed decades earlier for entirely different reasons. Heisenberg had independently reinvented a branch of mathematics in service of physics, and buried inside it was a consequence that would change everything. In 1927, Heisenberg published what is now called the Heisenberg uncertainty principle. In its most common form, it states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. Know exactly where something is, and its speed and direction become fundamentally unknowable. Know exactly how fast something is moving and in which direction, and its precise location blurs into a cloud. The product of the uncertainty in position and the uncertainty in momentum can never be less than a specific tiny constant Planck's constant divided by 4 pi. No matter how perfect your instrument, no matter how careful your experiment, no matter how advanced your technology becomes. This is not a statement about measurement error. It is not saying our tools are imprecise. It is not saying we need a better microscope. It is a statement about the universe, about what it means for a particle to have a definite position or a definite momentum at all. And this is precisely where the most common misunderstanding about the uncertainty principle lives, one that even many science communicators have accidentally reinforced over the years. People often describe the Heisenberg uncertainty principle by saying, when you try to measure a particle, the act of measuring disturbs it. You shine a photon of light on an electron to find out where it is, and the photon kicks the electron, changing its momentum. So, you know where it was, but not where it's going. The measurement itself causes the uncertainty. This version is intuitive. It makes physical sense, and it is incomplete and in important ways misleading. The disturbance explanation describes something real. Measuring a particle does often physically disturb it, but it misses the deeper point. Heisenberg's uncertainty is not about disturbance. It is about the nature of quantum states themselves. Here is the key. A quantum particle does not simultaneously have a definite position and a definite momentum to begin with. Before any measurement occurs, there is no hidden precise position being disturbed. Position and momentum in quantum mechanics are not two separate properties that a particle secretly possesses, and that we accidentally mess up when we look. They are complementary aspects of a single quantum state, and the quantum state genuinely cannot be sharp in both at once, not because of interference from measurement, but because that is what a quantum state is. The wave nature of matter makes this almost intuitive once you see it. A wave that is perfectly localized, a sharp spike at one precise point in space, is by the mathematics of waves composed of an infinite range of frequencies. And frequency is directly related to momentum. So, a perfectly located particle must have completely uncertain momentum. Conversely, a wave with a perfectly defined frequency and therefore perfectly defined momentum spreads infinitely across space with no definite position at all. Sharp position. Spread momentum. Sharp momentum. Spread position. You cannot have both because the mathematics of waves will not allow it. This is not a limitation of physics. It is a feature of waves. And matter at the quantum level is waves. Think about the consequences of this for a moment, because they reach far beyond physics laboratories. The uncertainty principle is in part why atoms are stable, why matter does not simply collapse. An electron in an atom is attracted to the positively charged nucleus at the center. If the electron could sit perfectly still at the nucleus, minimizing its potential energy, by getting as close as possible it would. But if the electron's position became perfectly defined, zero distance from the nucleus, then by the uncertainty principle its momentum would become completely undefined, meaning it would have enormous random momentum in some unpredictable direction. It would fly away instantly. The compromise the electron reaches the stable orbit we call a ground state is a balance between these two competing quantum demands. Get too close, and the position becomes too defined, forcing the momentum to explode. The electron settles into the lowest energy configuration that respects the uncertainty principle. Atoms are stable because the universe will not allow perfect precision. The quantum blur keeps electrons from collapsing into the nucleus. The uncertainty principle is not a frustrating limitation. It is the reason matter holds together. It is in a very real sense the reason you exist. Now the uncertainty principle applies to other pairs of quantities as well. Energy and time are another complementary pair. The more precisely defined the energy of a quantum state, the longer it must persist before being measured. The shorter the time available for a measurement, the more uncertain the energy. This has a remarkable consequence in particle physics. Quantum field theory, the framework that unites quantum mechanics with special relativity, predicts that particles can spontaneously appear from the vacuum of empty space, borrowing energy from nowhere, existing for an incredibly short time before annihilating back into nothing. These are called virtual particles, and they exist precisely because the time-energy uncertainty relation permits it. For an unimaginably short duration, the universe cannot tell whether the energy has been borrowed or not. This is not a theoretical curiosity. The Casimir effect, experimentally confirmed in 1997, demonstrates that virtual particles create a measurable force between two uncharged metal plates placed extremely close together in a vacuum. The plates are pushed toward each other by the pressure of quantum fluctuations in the space between them. Empty space pushes things. Because the uncertainty principle says, empty space cannot truly be empty. And on the grandest scale of all, many cosmologists believe that the large-scale structure of the universe, the distribution of galaxies, the great filaments and voids of cosmic matter, traces back to quantum fluctuations in the extremely early universe fluctuations, allowed by the uncertainty principle, which were then stretched and amplified by the rapid expansion of the cosmos in the first fraction of a second after the Big Bang. The uncertainty principle written into the foundations of matter at the smallest scale left its fingerprints on the largest structures we can see, from the stability of the atom to the map of the cosmos, from the reason your hand is solid to the reason the night sky is not uniform darkness. The uncertainty principle threads through all of it, quietly, relentlessly in the fabric of everything. Here is a question worth sitting with quietly. If even the universe itself cannot know two things at once, if the cosmos is built on fundamental, irreducible uncertainty, what does it mean to say something is truly completely known? Heisenberg once wrote, "The more we look, the less certain everything becomes." He did not write this with despair. He wrote it with something closer to wonder. The act of looking changes things. The observer is never truly separate from the observed. There is no view from nowhere, no perfect detached vantage point from which to see reality as it truly is, untouched and undisturbed. You are not a bystander. You were never a bystander. Every act of observation, every measurement, every interaction, every moment of contact between you and the world is a participation in reality, not a report on it. That is the deepest lesson of the observer effect. Not that measurement is difficult, not that instruments are imperfect, but that the boundary between the measurer and the measured is at the quantum level not a hard line at all. It is permeable, uncertain, itself a kind of superposition. And this brings us to a phenomenon that took that blurring of boundaries and extended it not just between an observer and a single particle, but between two particles separated by the entire width of a galaxy. A connection so strange, so instantaneous, so apparently impossible that the man who first predicted it refused to believe it was real. He called it a ghost, an absurdity, a sign that something was wrong with the theory. He was wrong. And the proof of that, a proof that arrived decades after his death, confirmed by a Nobel Prize in 2022, is one of the most beautiful stories in the history of science. That connection is called quantum entanglement, and the world it reveals a world where distance is not a barrier, where two particles can share a single fate across the void of space, is exactly where we are drifting next. Imagine you have a pair of gloves. You separate them without looking, place each one in a box and ship one box to New York and the other to Tokyo. When the box in New York is opened and you find a left-hand glove, you instantly know, without any signal, without any communication, that the glove in Tokyo is the right-hand one. That feels obvious, unremarkable. The gloves always had their identity. You simply didn't know which was which until you looked. Now, imagine something different. Imagine that the gloves did not have a definite handedness until the moment one of the boxes was opened, that before that moment each glove was genuinely neither left nor right, suspended in both possibilities simultaneously. And the instant the glove in New York becomes left-handed, the one in Tokyo becomes right-handed. Instantly. Not after a signal travels between them. Not after light crosses the ocean. Instantly, regardless of distance. That is not a story about gloves. That is quantum entanglement. And unlike the gloves, the physics behind it has been tested, confirmed, and awarded the Nobel Prize. The story of entanglement begins with a paper that was intended to destroy a theory and instead became one of the most cited documents in the history of physics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published what is now known as the EPR paper, named for their initials. Their argument was precise, logical, and delivered with the confidence of three men who believed they had caught quantum mechanics in a fatal contradiction. The argument went like this. Suppose two particles interact briefly and then separate. Quantum mechanics predicts that in certain cases, the quantum states of these two particles become linked entangled. The wave function that describes them is not two separate wave functions, one for each particle. It is a single shared wave function for the pair. Now, suppose you measure the spin of the first particle. Quantum mechanics says that before measurement, the spin is undefined, a superposition of up and down. The instant you measure it and find spin up, the second particle wherever it is, no matter how far away, instantly resolves to spin down. The correlated outcome appears simultaneously at both locations. Einstein, Podolsky, and Rosen found this deeply disturbing. Either they argued some kind of signal was traveling from one particle to the other faster than light, which Einstein's own relativity forbade, or the measurement of one particle somehow reached across space and changed the other instantaneously, which seemed equally impossible. Their conclusion was that quantum mechanics must be incomplete, that there must be hidden variables, some additional information encoded in the particles at the moment they were created, determining in advance how each particle would respond to any measurement, like the gloves in the boxes. The outcomes were decided from the beginning. We just didn't know them yet. Einstein called quantum entanglement spooky action at a distance, and he meant it as a criticism, a ghost story masquerading as physics, something that pointed to a gap in the theory, not a feature of reality. For nearly 3 decades, the debate remained mostly philosophical. There seemed to be no way to test it experimentally, no way to distinguish between a universe where particles carry hidden, predetermined answers and a universe where measurement outcomes are genuinely random and instantaneously correlated. Then in 1964, a physicist at CERN named John Stuart Bell published what many consider the most important result in the foundations of quantum mechanics. Bell's theorem, derived in a quiet afternoon of mathematics, according to some accounts, showed that the two possibilities Einstein had described were not equivalent. They made different measurable predictions. Bell proved that if particles carry hidden variables, if the outcomes are predetermined, then the correlations between measurements on separated particles must obey certain mathematical limits. He derived an inequality, a set of boundaries on how correlated the results could be. If the correlations exceeded those boundaries, hidden variables were ruled out. The universe would have to be doing something genuinely non-classical. The inequality became known as Bell's inequality, and it turned a philosophical argument into an experimental question. The first serious experimental tests were carried out in the early 1970s, most notably by John Clauser and his collaborators. Clauser, working against considerable skepticism from the physics establishment, his advisor reportedly told him the experiment would be a waste of time, measured the correlations between photons emitted in pairs from calcium atoms. The results violated Bell's inequality. The correlations were stronger than any hidden variable theory could produce. But the experiments had loopholes. Perhaps the detectors were not chosen randomly enough. Perhaps there was some subtle local signal between the detectors that wasn't being accounted for. The most celebrated series of experiments came in the early 1980s from Alain Aspect and his colleagues in Paris. Aspect's team closed the most important loophole by randomly switching the measurement settings on each detector while the photons were in flight, fast enough that no signal traveling at the speed of light could carry information from one detector to the other in time. The correlation still violated Bell's inequality. The universe, it seemed, was genuinely non-local in some deep sense. The results of measurements on separated particles were correlated in ways that exceeded any local predetermined explanation. And then, in 2022, the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments using entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. The Nobel Committee was explicit these experiments confirmed that the quantum world cannot be described by hidden variables. Nature is, in a precise technical sense, non-local. Einstein's intuition that the universe must be built on local, definite, predetermined facts was wrong. Now here's the most common and most important misunderstanding about entanglement, one that even enthusiastic science writers sometimes stumble into. Entanglement is not faster-than-light communication. It cannot be used to send information from one place to another faster than the speed of light. It does not violate relativity. Here is why. When you measure the entangled particle in New York and find spin-up, you instantly know the particle in Tokyo is spin-down. But the result you got in New York was random. You had no control over whether you would get spin-up or spin-down. The outcome was not predictable in advance. So, you cannot use that result to encode a message because you cannot choose what outcome you will get. The person in Tokyo also gets a random result, spin down, in this case. On its own, their result looks like noise, just a random quantum outcome. The correlation between the two results only becomes apparent when the two experimenters later compare notes using ordinary classical communication, a phone call, an email, a letter, which travels no faster than light. Entanglement creates correlations, not communication. The connection is real, but it carries no signal, no information, no message. It is in some sense a kind of togetherness without transmission, a shared fate without a shared medium. Anton Zeilinger, in his Nobel lecture, described entanglement as the fundamental feature that distinguishes quantum mechanics from all classical theories. Not the uncertainty principle, not superposition. Entanglement. The possibility that two particles, once they have interacted, remain part of a single quantum description no matter how far apart they travel. The Austrian physicist made a point that is worth dwelling on. He said that entanglement is not about information traveling between particles. It is about the world being structured differently than we imagined. The assumption that two distant objects are always fully independent, that the state of the particle in Tokyo is completely unconnected to the state of the particle in New York once they are separated, is simply not how the universe works. At the quantum level, separation is not always the same as independence. The universe keeps certain things connected, not through a wire, not through a force, through the fabric of the quantum state itself. Have you ever felt inexplicably connected to something or someone across a distance? Not mystically, but in that strange way where two things seem to belong to the same story, even when they are far apart. Quantum entanglement will not explain human experience, but perhaps it offers a small, gentle reminder that the universe does not always honor the boundaries we draw between things. Now, entanglement has become the engine driving one of the most remarkable technological frontiers of the 21st century. Quantum computing the field, trying to build computers that process information using superposition and entanglement rather than classical bits, relies fundamentally on entanglement to perform certain calculations exponentially faster than any classical machine could. Quantum cryptography, quantum key distribution, uses entanglement to create communication channels, where any eavesdropping attempt is physically detectable because measuring an entangled particle inevitably disturbs it. The laws of physics, not the laws of mathematics, become the guarantee of security. Quantum teleportation demonstrated experimentally for the first time in 1997 by Zeilinger's group in Vienna, uses entanglement to transmit the complete quantum state of a particle from one location to another without the particle itself traveling. Not matter teleportation in the science fiction sense, but the transfer of quantum information perfectly across a distance. As of 2024, researchers have teleported quantum states over distances exceeding 1,000 kilometers using satellites to maintain the entangled links. The technology of entanglement is real, growing, and beginning to reshape how we think about communication, computation, and security in ways that would have seemed magical even 50 years ago. And all of it rests on a foundation that Einstein dismissed as a ghost story, a spooky action, an impossibility that turned out to be a feature. What the EPR paper was meant to prove, that quantum mechanics was incomplete, ended up through Bell's theorem and decades of experiments proving something even stranger. That reality itself is more deeply connected, more stubbornly non-local, more resistant to the comfortable idea of independent isolated objects than any of them had imagined. Einstein was one of the greatest scientific minds in history. He was wrong about this. And the lesson in that is not a criticism of Einstein. It is a lesson about the nature of discovery. Even the most brilliant, most careful, most deeply intuitive thinker can look at a new piece of mathematics and mistake a feature for a flaw, can see strangeness and call it incompleteness, can feel the universe pulling in a direction that seems impossible and pull back. The universe does not care about comfort. It is what it is, even when what it is defies every expectation we have built over a lifetime. Entanglement tells us that two things once connected are never fully separate again, that the universe maintains relationships across distance in a way that has no classical analogy, that some threads once woven together do not simply unravel when pulled apart. But here, a deeper question rises. If particles can be entangled, if quantum states can be shared, correlated spread across space, then what happens to those states when they interact with the larger world around them? When the universe measures itself not through a controlled experiment in a laboratory, but simply through the endless, constant, irreversible contact between particles and their environment. Why doesn't your coffee cup tunnel through the table? Why doesn't the chair beneath you exist in a superposition of all its possible positions? Why do the quantum rules that govern electrons and photons seem to vanish entirely when applied to the objects of everyday life? The answer to that question lives in a process that is both mundane and profound. A process happening inside every object you can see, inside every atom of the air you are breathing right now. A process called quantum decoherence. And what it reveals about the line between the quantum world and the classical world, a line that may not be a line at all, is precisely what we are about to explore. Your coffee cup is sitting on the table right now, solid, definite, exactly where you left it. It is not in two places. It is not spinning in all directions at once. It is not shimmering in a fog of quantum probabilities. It is just there, ordinary, obvious. And yet, every single atom inside that cup, every electron orbiting every nucleus in the ceramic and the coffee and the air touching its rim, is governed by the same quantum laws that make particles pass through two slits at once, the same laws that produce superposition, the same laws that allow entanglement. So, why doesn't your coffee cup behave like a quantum object? Why doesn't it tunnel through the table? Why doesn't it exist in a superposition of positions until you look at it? The answer is one of the most profound and least understood ideas in all of modern physics, and it lives at the boundary between the quantum world and the world you can see and touch. A boundary that the deeper you look seems less like a wall and more like a slow, irreversible dissolving. The process is called decoherence, and the story of how physicists discovered it and what it tells us about why reality looks the way it does begins with a problem that haunted quantum mechanics almost from the day it was born. The measurement problem. That is what physicists called it. And for decades it sat at the heart of quantum theory like a splinter no one could remove. The problem is this. The Schrödinger equation. The master equation of quantum mechanics is beautiful, precise, and deterministic. Given the wave function of a system at any moment, it tells you exactly how the wave function evolves over time. No randomness, no ambiguity. A perfect, smooth, continuous evolution. But the moment a measurement occurs, the moment a quantum particle interacts with a detector, a screen, a photographic plate, or any macroscopic measuring device, something different happens. The smooth wave function, which was spread across multiple possibilities, suddenly resolves into a single definite outcome. The superposition collapses. One result becomes real, the rest disappear. This collapse is not described by the Schrödinger equation. It is simply declared to happen as an additional rule layered on top of the theory. The wave function evolves smoothly according to one rule until a measurement happens, at which point a completely different rule takes over. And the second rule produces a random outcome with probabilities given by the wave function. Where does the collapse come from? What triggers it? Why does the smooth quantum world suddenly snap into a definite classical outcome when a measurement is made? This is the measurement problem. And for the first 50 years of quantum mechanics, most physicists dealt with it by not dealing with it. Niels Bohr's Copenhagen interpretation essentially said, do not ask what the wave function really is. Do not ask what happens during collapse. Just use the rules to calculate probabilities, compare with experiment, and accept that the act of measurement is the boundary between the quantum and the classical. The boundary itself was not to be analyzed. This was profoundly unsatisfying to many physicists. John Wheeler, David Bohm, Everett, whose many worlds interpretation we visited earlier, all felt that declaring a special measurement process outside the Schrödinger equation was an admission that the theory was incomplete. The resolution, or at least the most widely accepted modern understanding, came gradually over the second half of the 20th century. It goes by the name quantum decoherence, and it shifts the question from when does the wave function collapse to why do quantum systems stop behaving quantum mechanically when they become large? Here is the core idea. A quantum superposition is extraordinarily fragile. It depends on the different components of the superposition, the spin up and spin down, the here and there, the alive and dead, remaining coherent. Coherent means that the different components still have a definite phase relationship with each other. They can still interfere. They can still produce quantum effects. When a quantum particle is isolated alone in a carefully controlled laboratory shielded from vibration and thermal noise and stray electromagnetic fields, it can maintain its coherence. Its superposition is real and measurable. The interference patterns appear. But the moment that particle interacts with its environment, with air molecules, with photons from the room, with the vibrations of the measuring device, with the thermal noise of ordinary matter at room temperature, the superposition becomes entangled with an astronomically large number of environmental particles. And as the quantum information spreads out into the environment, becoming encoded in millions upon millions of particles that no experiment could ever track or measure, the coherence is lost. The interference between the superposition components vanishes, exponentially fast. In a time so short, it is almost unmeasurable. The superposition does not disappear. Strictly speaking, the wave function of the entire system, particle plus environment, is still a superposition. But the components of the superposition are now so thoroughly entangled with different orthogonal states of the environment that they can no longer interfere with each other. For any practical purpose, for any measurement, any instrument could ever make the different branches of the superposition are invisible to each other, sealed off, effectively separate. This is decoherence. The quantum coherence leaks into the environment. The ability to observe quantum interference dissolves. What remains looks from any accessible vantage point, exactly like a classical probability distribution, not a superposition, just ordinary uncertainty about which of several definite outcomes occurred. The timescale for decoherence is staggeringly fast for macroscopic objects. For a single electron in vacuum, coherence can be maintained for measurable periods of time. For a molecule in air at room temperature, decoherence occurs in roughly 10 to the minus 13th seconds. For a dust particle, decoherence occurs in roughly 10 to the minus 31st seconds. For an object the size of a coffee cup, the coherence time is so incomprehensibly short, so many orders of magnitude beyond any possibility of measurement, that quantum effects are completely and irreversibly suppressed before they could ever be observed. Your coffee cup decoheres essentially instantly, not because it lacks quantum properties, because it is too large, too warm, and too entangled with the environment for those properties to manifest as anything observable. This is why you do not see quantum weirdness in everyday life, not because everyday objects obey different laws, but because the laws are the same, and at macroscopic scales, decoherence overwhelms quantum coherence so completely and so rapidly that classical behavior emerges as if by necessity. Now here is the subtle but crucial distinction that is worth sitting with carefully, because it is where many popular explanations take a wrong turn. Decoherence explains why quantum systems stop behaving quantum mechanically when they interact with large environments. It explains why the interference effects vanish. It explains why a large object always seems to have a definite position, rather than a spread-out wave function. But decoherence alone does not fully solve the measurement problem. What decoherence gives you is a quantum state that looks like a classical mixture, a collection of possible outcomes with definite probabilities. What it does not tell you is why one particular outcome is the one that actually occurs when a measurement is made. The mathematics after decoherence describes a system that has many possible results with specific probabilities, but it does not select one result and discard the others. That selection, the definite click of the detector, the specific position of the particle, the single outcome that enters your experience remains in some interpretations unexplained. In the many worlds framework, all the outcomes continue to exist in separate branches of the wave function. In other interpretations, some additional principle selects a single outcome. In the instrumentalist view, the question itself is illegitimate. Quantum mechanics predicts probabilities, not mechanisms. And asking for the mechanism of selection is asking the wrong question. The measurement problem has not been fully solved. It has been clarified, refined, and partially addressed by decoherence. But the deepest question, why this outcome, rather than another, remains one of the open wounds in the foundations of physics. What decoherence has given us, however, is something enormously valuable, a precise quantitative experimentally testable account of how quantum mechanics transitions into classical mechanics. Not a mysterious boundary, not a wall between worlds, but a smooth physically explicable process by which quantum coherence dissolves into the environment and classical behavior emerges. And the experimental evidence for decoherence is remarkable. In the 1990s and 2000s, physicists became able to engineer mesoscopic systems, objects somewhere between the quantum and classical scales, and directly observe the transition from quantum to classical behavior as those systems were exposed to increasingly noisy environments. They watched superpositions decay. They measured decoherence timescales. They confirmed the theoretical predictions with extraordinary precision. In 1996, Serge Haroche and his colleagues in Paris trapped microwave photons inside a superconducting cavity and watched in real time as a quantum superposition of photon states decohered when exposed to thermal noise. They measured the gradual decay of quantum coherence, the slow fading of the wave function's quantum character, as it entangled with the environment. Haroche won the Nobel Prize in Physics in 2012, in part for this work. Decoherence is not a philosophical position. It is a measured, confirmed physical process. And here is perhaps the most quietly astonishing implication of all: the classical world. The world of solid objects, definite positions, ordinary cause and effect is not more fundamental than the quantum world. It is not the foundation that quantum mechanics is built upon. It is the quantum world as seen from the inside of a system that has lost its coherence. Classical reality is what quantum mechanics looks like after decoherence has done its work. The ordinary world is not the ground floor of the universe. It is an emergent property, a pattern that arises in the quantum foam when the quantum foam gets large enough and warm enough and entangled enough with itself. Solid is not fundamental. It is derived, a consequence. A beautiful, stable, persistent consequence, but not the deepest thing. Does that change how you feel sitting in the quiet right now? Knowing that the solidity beneath you is not bedrock, that it is the universe's way of averaging over its own uncertainty into something you can rest on. There is a strange comfort in that, if you let yourself feel it. The ordinary world did not replace the quantum world. It grew from it. It is made of it. The strangeness is still there underneath everything humming, very quietly. And this brings us to a phenomenon that lives right at that edge where the quantum strangeness seeps through into a consequence so tangible, so physically real, that without it, the sun would not shine and life on Earth would never have begun. A phenomenon where the quantum wave function does not merely fade into classical behavior, but actively uses its wave nature to do something that classical physics says is completely, absolutely, flatly impossible. A particle that arrives at a wall it cannot climb, and passes through anyway. That is quantum tunneling. And the history of how it was discovered and the extraordinary list of things in the universe that depend on it is exactly where we drift next. Right now, inside the sun, something impossible is happening. Two protons each carrying a positive electrical charge, each furiously repelling the other with a force that grows stronger. The closer they get are somehow against all classical reason touching, merging, fusing, releasing the energy that has warmed every living thing on this planet for 4.5 billion years. By the mathematics of classical physics, this should not happen. The temperature at the sun's core, about 15 million degrees Celsius, is not nearly hot enough to give those protons the energy they would need to overcome the electrical barrier between them. Classical physics calculates that the sun should be too cold to shine, that nuclear fusion at the sun's core should be essentially impossible, and yet the sun shines, has shone for billions of years, will shine for billions more. The reason, the quiet, extraordinary reason, is that protons are not classical objects. They are quantum objects, and quantum objects do not need to climb over a barrier. They can borrow their way through it, appear on the other side without ever passing through the forbidden space in between. This is quantum tunneling, and without it, there would be no stars, no sunlight, no warmth, no photosynthesis, no life. The universe would be a cold, dark, sterile place. The history of tunneling begins in 1928 with a young Russian-American physicist named George Gamow working in Göttingen. Gamow was brilliant, irreverent, and famously difficult to take seriously. He was known for practical jokes, outrageous humor, and a personality so outsized that his colleagues often underestimated the depth of his thinking. He was trying to explain a problem that had been bothering nuclear physicists for years: radioactive decay, the process by which unstable atomic nuclei emit particles and transform into other elements, happened at rates that classical physics simply could not account for. Specifically, alpha decay, in which a nucleus emits a cluster of 2 protons and 2 neutrons called an alpha particle. Inside a nucleus, the alpha particle is held in place by the strong nuclear force. To escape, it would need to pass through an energy barrier, a wall of repulsive electrical force that classical physics said it could not overcome. The alpha particle simply did not have enough energy to climb over the wall, and yet, experimentally, nuclei decayed. Alpha particles escaped, at rates that could be precisely measured and that followed a specific mathematical pattern. Gamow applied the newly developed mathematics of quantum mechanics to the problem. He treated the alpha particle as a quantum wave spreading out in space with a small but non-zero amplitude extending through the classically forbidden region, the energy barrier, and beyond. He calculated the probability that the wave function would leak through the barrier and emerge on the other side. The numbers match the experimental decay rates beautifully, not just qualitatively, quantitatively. The tunneling probability his calculation produced explained exactly why different radioactive isotopes decay at the rates they do, why uranium-238 has a half-life of 4.5 billion years, why polonium-212 has a half-life of less than a microsecond. The thickness and height of the energy barrier, combined with the mass and energy of the tunneling particle, determines the probability of escape. Gamow's formula captures all of it. Independently and almost simultaneously, the British physicists Ronald Gurney and Edward Condon published the same idea in a paper submitted just weeks after Gamow's. The tunneling model of radioactive decay was confirmed almost immediately by the physics community. It was one of the first great experimental validations of the new quantum mechanics, and it pointed to something genuinely revolutionary. Matter passes through barriers it classically cannot cross, not because the barrier isn't real, but because quantum particles are waves, and waves don't stop at walls the way billiard balls do. A wave encountering a barrier is partially reflected and partially transmitted. If the barrier is thin enough and the wave is large enough, some amplitude leaks through. And where there is amplitude, there is probability. And where there is probability, sometimes things happen. Now here's the question that draws so many people in, and also the place where the most common misunderstanding arises. People often imagine quantum tunneling as something like a magic teleportation trick. The particle disappears on one side of the barrier and reappears on the other, skipping through solid matter like a ghost walking through a wall. They imagine the particle momentarily blinking out of existence and materializing somewhere else. This is not what happens. And the actual picture, while harder to visualize, is far more beautiful. The particle before tunneling does not have a definite position. It exists as a wave function, a spread-out probability distribution on one side of the barrier. That wave function has a long tail that extends into and through the barrier, even though the particle's energy is below the barrier height. The amplitude in the barrier region decays exponentially. With distance, it drops off very quickly, but it never reaches exactly zero. On the far side of the barrier, there is always a small but non-zero amplitude, a whisper of probability. When the particle is detected, there is a small but real chance that it will be found on the far side. Not because it traveled through the barrier, not because it went around it, not because it momentarily ceased to exist and reappeared, but because its wave function extended beyond the barrier from the very beginning, and the measurement revealed an outcome that was always quietly possible. Tunneling is not teleportation. It is the consequence of the wave nature of matter meeting the probabilistic character of quantum mechanics. It is the universe's way of saying that impossible is a word that applies to classical particles, not to quantum waves. And the range of phenomena that depend on quantum tunneling is, when you lay it out, breathtaking. The sun, every star in the sky, stellar fusion. The process that powers every sun in every galaxy in the observable universe relies on protons tunneling through the Coulomb barrier, the electrostatic repulsion between positive charges. Without tunneling, the temperature at stellar cores would need to be roughly 1,000 times higher than it actually is to sustain fusion classically. No star could maintain that temperature. No star would ever form. The night sky would be cold and dark in every direction. Nuclear fusion in stars is the engine of the universe, and quantum tunneling is the key that starts the engine. Radioactive decay. The very process Gamow first explained is the source of much of the internal heat of the Earth. Radioactive isotopes in the planet's mantle and core decay by tunneling, releasing heat that drives convection, powers the magnetic field, and fuels volcanic activity. The geology of our planet, its mountains, its oceans, its breathable atmosphere, maintained partly by volcanic outgassing over billions of years, is connected through a long chain of causes to quantum tunneling. The chemistry of life itself may depend on it. DNA, replication, and mutation rates are influenced in ways researchers are still actively studying by the tunneling of hydrogen atoms, protons, along hydrogen bonds within the double helix. Some researchers in the field of quantum biology propose that certain enzymatic reactions in living cells proceed at rates that classical chemistry alone cannot explain, and that proton tunneling through energy barriers and enzyme active sites contributes to the catalytic efficiency of life's molecular machinery. The field is young, and the evidence is still accumulating, but the possibility that quantum tunneling plays a role in the chemistry of life is not a fringe idea. It is an active area of serious scientific research. And then there is the technology you use every day. The scanning tunneling microscope invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM Zurich, work that earned them the Nobel Prize in 1986, works by measuring the tiny electrical current produced when electrons tunnel across the gap between a sharp metal tip and a surface being imaged. The tip is brought so close to the surface within a fraction of a nanometer that the electron wave functions overlap, and electrons tunnel across the vacuum gap. The tunneling current is extraordinarily sensitive to the gap distance. Move the tip 1/10 of a nanometer closer, and the current changes by an order of magnitude. This sensitivity allows the microscope to image individual atoms on a surface, to see matter at the atomic scale directly for the first time in history. The images produced by scanning tunneling microscopes, photographs, and a genuine sense of individual atoms remain among the most astonishing things human technology has ever produced. The ability to see an atom, not infer it, not calculate it. See it its quantum wave function extending slightly above the surface like a tiny hill. Binnig and Rohrer showed those images to the world in 1981, and the response in the physics community was something close to awe. Flash memory. The technology inside every USB drive, every SSD hard drive, every smartphone stores data by trapping electrons on a piece of semiconductor called a floating gate, isolated by a layer of silicon dioxide that acts as an insulating barrier. Writing data to flash memory involves forcing electrons through this insulating barrier. Reading data involves detecting whether electrons are present or absent. Both processes, writing and reading, use quantum tunneling. The insulating layer is thin enough that electrons can tunnel through it when a voltage is applied. Every photograph you have saved, every document you have written, every message you have sent from a phone or a laptop, stored and retrieved using quantum tunneling, using the same phenomenon that makes radioactive nuclei decay and stars shine. The walls, it turns out, were never as solid as they looked. Here is something worth pausing on, because it touches something deeper than physics. Tunneling is at its core a statement about the relationship between probability and impossibility. In classical mechanics, impossible is an absolute. An object without enough energy to cross a barrier cannot cross the barrier. End of story. The outcome is zero. Forbidden. Quantum mechanics does not recognize absolute zeros of probability, not for processes that are merely energetically unfavorable rather than violating fundamental conservation laws. If a process can happen without breaking the rules of conservation of energy or momentum quantum mechanics assigns it a probability. That probability might be vanishingly small. It might require waiting longer than the age of the universe, but it is not zero. And a non-zero probability given enough time and enough particles becomes an inevitability. The sun shines because of non-zero probability. Life exists because of non-zero probability. The atoms inside your body were forged in stellar cores where non-zero probability made the impossible routine across billions of years and billions of stars. The lesson of quantum tunneling is not merely technical, it is almost philosophical. The universe does not build absolute walls. It builds barriers of varying thickness and height, and it assigns probabilities to everything that isn't outright forbidden. Nothing that is merely unlikely is permanently blocked. Given the right conditions, the right scale, the right time scale, the right quantum wave function, the improbable becomes actual. The impossible very quietly becomes the foundation of everything. There is one more consequence of tunneling that sits at the very edge of what we currently understand. Physicists have calculated that even matter itself, large stable structures like protons, like atomic nuclei, should over incomprehensibly vast timescales eventually tunnel into lower energy configurations. The proton itself, some theories suggest, should have a finite half-life, though longer than the current age of the universe by many orders of magnitude. Whether this is true is an open experimental question, but the calculation exists. The possibility is real. Even the solid matter of the universe is in principle subject to the same probabilistic dissolution that governs every quantum process. Sitting still patient over time scales, the human mind cannot hold everything that exists, is slowly, imperceptibly, probabilistically dissolving into something else. The walls are not really there, they never were. And having passed through those walls, having seen what quantum tunneling does to our ideas of barrier and boundary and the absolute, we arrive at a question that has been building quietly since the first pages of our journey tonight. If quantum mechanics is this precise, this confirmed, this stunningly successful at describing the universe, why do so many of its implications remain contested and unresolved after 100 years? Why do physicists still argue passionately and without resolution about what quantum mechanics means? The answer lives in one of the oldest and strangest mysteries in the theory, the question of what happens the moment reality crystallizes from probability. The moment the wave function encounters the world and chooses or seems to choose a single definite outcome from a sea of possibilities. The moment that some physicists believe splits the universe in two, and others believe is simply the universe updating its own ledger. That moment has a name, and the mathematics behind it, the story of how probability becomes fact, how the quantum becomes the classical, how one answer emerges from infinite possibility is exactly where we find ourselves now. There is a place in the universe that has nothing in it. No atoms, no molecules, no light, no heat, no dust, no air. Scientists have created it in laboratories, a chamber so perfectly evacuated that fewer particles remain inside than exist in the deepest reaches of interstellar space. A void so complete that classical physics would describe it as the absence of everything, zero, emptiness, the closest thing to true nothingness that the physical world allows. And that void is alive. It seethes, it hums, it flickers with an endless restless energy that cannot be switched off, cannot be drained, cannot be stilled. Particles appear from nowhere and vanish back into nothing, billions of times per second in every cubic centimeter of that perfect emptiness. Forces flicker into existence and dissolve. Energy borrows itself from the future and repays the debt before anyone can notice. This is not a metaphor. It is not a poetic description of something unmeasurable. It is a confirmed, experimentally verified feature of the universe that has been measured in laboratories used to calibrate the most precise instruments in science and built into the foundations of the most accurate physical theory ever constructed. The quantum vacuum is not empty, and the story of how physicists discovered what nothing actually contains may be the most quietly astonishing chapter in the entire history of science. To understand the quantum vacuum, we need to step beyond ordinary quantum mechanics into the framework that extended it, a theory called quantum field theory. And the story of how it was born is one of intellectual struggle, personal rivalry, and a mathematical crisis that nearly broke the field before it was resolved by an insight so brilliant and so strange that the physicists who developed it were themselves uncomfortable with it. In the late 1920s and early 1930s, physicists realized that ordinary quantum mechanics, the theory of Schrödinger and Heisenberg, had a problem. It described the particles well, but it was not compatible with Einstein's special relativity. The Schrödinger equation, treated time differently from space, which violated the symmetry that relativity required. And quantum mechanics had no natural way to describe particles being created or destroyed, which experiments were beginning to show happened all the time at high energies. The first step toward a solution came from Paul Dirac in 1928. Dirac was perhaps the most mathematically gifted of all the quantum pioneers, a man of such extraordinary precision and economy of thought that his colleagues told a joke the unit of speech should be called a Dirac, defined as 1 sentence per hour. He derived a relativistic equation for the electron, now called the Dirac equation, that combined quantum mechanics with special relativity in a way that was mathematically elegant and physically profound. But the Dirac equation came with a strange and disturbing prediction. It had 2 sets of solutions. One set described the electron as physicists knew it. The other set described something with negative energy, an electron that fell into an ever deeper energy pit, radiating energy endlessly unstable with no lower bound. That would be catastrophic. Atoms would be unstable. Matter would collapse. The universe would not exist. Dirac proposed a solution so audacious that it took time for his colleagues to accept it. He suggested that the negative energy states were not empty. They were already full, filled with an infinite sea of electrons in negative energy states, electrons that could not fall any deeper because every available state was already occupied. The vacuum on Dirac's picture was not nothing. It was a completely filled sea of invisible particles. And if one of those negative energy electrons were struck by a sufficiently energetic photon, it could be knocked out of the sea, leaving behind a hole, a gap in the otherwise full negative energy sea. That hole would behave to a physicist observing it exactly like a particle with positive energy and positive charge, the opposite of an electron. In 1932, Carl Anderson at Caltech observed exactly such a particle in cosmic ray experiments. He called it the positron, the antiparticle of the electron, the first particle of antimatter ever detected. Dirac's mathematical hole in the vacuum had a physical reality. Matter and antimatter were born together from the mathematics of a filled nothingness. The vacuum was not empty. It was the ground state of an infinite sea. This picture was later replaced by a more sophisticated and mathematically precise framework, but the essential insight remained. The vacuum is a state, the lowest energy state of a quantum field. And that state is not nothing. It is something, a something that has energy fluctuations and measurable physical consequences. Quantum field theory, the framework that eventually unified quantum mechanics with special relativity into a coherent picture, describes the universe not as a collection of particles moving through space, but as a collection of fields that permeate all of space. The electron field, the photon field, the quark field, and many others. These fields exist everywhere, even in regions of space with no particles present. Particles in this picture are not fundamental objects. They are excitations of their underlying fields, ripples, peaks, localized disturbances in a field that is always present. An electron is not a tiny ball. An electron is a vibration in the electron field. A photon is a vibration in the electromagnetic field. The distinction sounds subtle, but its implications are enormous. Because if the fields are always present even in empty space, and if quantum mechanics requires that fields obey the uncertainty principle, then the field values at every point in space are subject to quantum uncertainty, just like the position and momentum of a particle. And the uncertainty principle means those field values can never be precisely zero. They fluctuate, constantly, randomly. In every corner of space at every moment, the quantum fields are shivering with zero-point energy, the irreducible energy of quantum uncertainty that cannot be removed, no matter how cold or empty or undisturbed the system becomes. These fluctuations are called quantum vacuum fluctuations, and they produce real measurable particles, pairs of a particle, and its antiparticle flickering into existence, persisting for a time, allowed by the energy-time uncertainty relation. and then annihilating each other back into the vacuum. These are the virtual particles mentioned briefly in our earlier discussion of the uncertainty principle, and here we can see where they live and what gives rise to them. They are real enough to be measured. In 1947, the American physicist Willis Lamb discovered a tiny but precise difference in the energy levels of the hydrogen atom, a difference that classical physics and even the original Dirac equation predicted should not exist. This difference, now called the Lamb shift, arises because the electron in a hydrogen atom is constantly interacting with the quantum vacuum fluctuations of the electromagnetic field. The virtual photons of the vacuum tug on the electron, shifting its energy levels by a tiny but specific amount. The Lamb shift is one of the most precisely measured quantities in all of physics. Quantum electrodynamics. The version of quantum field theory that describes electrons and photons predicts the Lamb shift to an accuracy of better than 1 part in a trillion. The agreement between theory and experiment is so precise that if you scaled it to the distance from here to the nearest star, the error would be smaller than the width of a human hair. The quantum vacuum is not a philosophical abstraction. It is a physical entity whose effects have been measured to 12 decimal places. And then there is the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948, and experimentally confirmed with high precision by Stephen Lamoureux in 1997. Casimir was thinking about 2 perfectly conducting metal plates placed extremely close together in a vacuum. The vacuum fluctuations of the electromagnetic field fill all of space, including the gap between the plates. But inside the gap, only certain wavelengths of virtual photons can fit those whose wavelengths divide evenly into the gap distance. Outside the plates, all wavelengths are present. This means there are more vacuum fluctuations pushing the plates together from outside than there are virtual photons pushing them apart from between them. The imbalance creates a net attractive force between the plates, pushing them toward each other across the vacuum. The plates are pushed together by the pressure of nothing, by the force of the vacuum itself, expressing its quantum nature in a measurable, calculable, experimentally confirmed way. The Casimir force has now been measured in hundreds of experiments and is consistent with the quantum field theory prediction at the level of a few percent, limited primarily by the difficulty of machining perfectly flat surfaces at nanometer scales. Nothing pushes, nothing attracts, nothing has weight and pressure and energy. Here's a question worth sitting with, in the quiet. If the vacuum, the emptiest possible state of the universe, is seething with energy and fluctuation, what does that mean for the total energy of the universe itself? This question leads directly to one of the most embarrassing and most fascinating open problems in all of physics. When physicists try to calculate the energy density of the quantum vacuum, the amount of energy contained in a cubic centimeter of empty space based on the quantum field theory of vacuum fluctuations, they get an answer that is, depending on the assumptions used, somewhere between 40 and 120 orders of magnitude larger than the energy density of the observed universe, a factor of 10 to the power of 40, or 10 to the power of 120. A discrepancy so enormous it beggars description. The largest discrepancy between theory and observation in the history of science by a margin that makes every other unsolved problem look trivially small. This problem is called the cosmological constant problem. It has been called, without exaggeration, the worst theoretical prediction in the history of physics. And despite decades of effort by some of the most brilliant minds in theoretical physics, no one has solved it. No one knows why the vacuum energy of the universe is as small as it appears to be. No one knows what mechanism, if any, cancels most of the theoretically predicted vacuum energy and leaves only the small remainder that observations suggest. It is a wound in our understanding of nature, an open question of the deepest kind sitting right at the intersection of quantum mechanics and cosmology, quietly reminding every physicist who thinks about it that for all the extraordinary success of quantum field theory, something fundamental is still missing from our picture of the universe. And there is another vacuum phenomenon that connects the smallest scales to the largest structure in existence. In the very early universe, in the first fraction of a second after the Big Bang, cosmologists believe the universe underwent a period of extraordinarily rapid expansion called cosmic inflation. During inflation, quantum vacuum fluctuations in the energy fields driving this expansion were stretched by the expanding space to macroscopic scales. Those fluctuations, those tiny random shiverings of quantum fields in the primordial vacuum, became the seeds of structure in the universe. They grew over hundreds of millions of years into the first galaxies, the first stars, the great cosmic web of filaments and voids that constitutes the large-scale structure of the observable universe, the pattern of galaxies in the night sky, the great cosmic voids between them, the specific texture of the universe on its largest scales. These structures trace back through a chain of physics spanning 14 billion years to quantum fluctuations in the vacuum of the primordial universe, to nothing shivering. We are in some profound sense the children of vacuum fluctuations. The ordered, complex living world emerged from the random quantum noise of the earliest moments, structure from uncertainty, pattern from fluctuation, existence from the restless, irreducible energy of nothing. What remains after tunneling after vacuum fluctuations, after entanglement and decoherence and superposition, and the uncertainty principle is a picture of reality that is stranger and richer and more deeply connected than anything classical physics imagined. A universe where nothing is ever truly empty, where walls are probabilities rather than absolutes, where particles share fates across space, and where the very act of looking changes what is seen. 9 quantum laws. 9 windows into a world that has been here all along, underneath everything obeying rules so different from the ones we grew up trusting, that accepting them requires a kind of quiet surrender, a willingness to hold uncertainty gently, rather than demanding the comfort of the definite. And now, having wandered through all of it, from the crisis that shattered classical physics to the seething nothingness of the quantum vacuum, there is one final thing left to do. Not to summarize, not to conclude, but to rest with what we have found, to let the strangeness settle the way light settles on water just before the sun goes down. To find the place where all of this, every paradox, every revelation, every beautiful unsolved mystery meets the quiet of a night that is ready to receive it. That place is just ahead, and it is in its own way the most important part of the journey we have taken tonight. We have traveled a long way tonight. We began in the late 1800s, standing inside a world that believed it had almost figured everything out. A clockwork universe, precise and predictable, running on rails that Newton laid down and Maxwell polished to a shine. A world where the rules were clear, the future was calculable, and the only work left was to measure things more precisely. And then the light misbehaved. A beam passed through 2 slits and drew stripes that no particle should draw. A single electron traveling alone interfered with itself. An atom emitted energy in packets rather than streams, and one by one, with growing speed and growing strangeness, the rails came up. The clockwork stopped. The comfortable certainty that had held for 2 centuries quietly crumbled, not into chaos, but into something far more interesting, into probability, into superposition, into entanglement and uncertainty and tunneling and vacuum fluctuations that hum in every corner of empty space, into a universe that turned out to be underneath everything radically, gloriously, irreducibly strange. Think about what we found together tonight. We found that a particle, a single quantum of matter, can exist in multiple states simultaneously holding contradictions, in suspension, the way a held breath holds both stillness and the need to move. We found that measuring it, simply looking, collapses that suspension into a single outcome, as if the universe were waiting for a witness before it decided what to be. We found that 2 particles, once entangled, share a fate that no distance can sever, that the universe keeps certain connections alive across spaces so vast that light itself takes billions of years to cross them. We found that the act of knowing something about a particle changes what that particle does. Not because our instruments are clumsy, but because knowledge and physical reality are not as separate as we imagined. We found that barriers are not walls, but gradients of probability, that quantum tunneling allows the impossible to happen slowly, steadily, persistently, until the sun itself burns with energy that classical physics said it could not produce. And we found that the vacuum, the emptiest possible place, the closest thing to nothing that physics can construct, is not nothing at all. It seethes with energy. It whispers with virtual particles. It pushes metal plates together across a gap of pure emptiness because the universe refuses to let nothing mean nothing. Here is the thing that I find most extraordinary about all of it. These are not exotic phenomena confined to particle accelerators and theoretical journals. They are happening right now in the room where you are resting, in the atoms of the air, in the electrons orbiting every nucleus in the walls around you, in the photons reaching your eyes from whatever dim light remains in your space, in the molecules of the neurotransmitters that are even now settling your mind towards sleep. You are not observing a quantum universe from a comfortable classical distance. You are made of the quantum universe. You are one of its arrangements, one of the ways it chose or didn't exactly choose, but found through probability and time to organize itself into something that can wonder about its own nature. That is not a small thing. That is perhaps the most remarkable thing there is. In 1931, Werner Heisenberg wrote in a letter to a colleague, "The more we know about the universe, the more it seems to be a thought." He was not descending into mysticism. He was a physicist responding with genuine surprise to what the mathematics was telling him. The further physics reached into the foundations of matter, the less it resembled the hard, solid, objective world of common sense, and the more it resembled something fluid, relational, dependent on the act of inquiry in ways that the billiard ball universe of Newton never was. Niels Bohr, who spent more of his life inside the quantum world than perhaps anyone, said near the end of his career that the lesson of quantum mechanics was not that the world is strange. It was that our concepts of it are limited, that the words we use, particle wave position, path, cause, effect, are borrowed from the macroscopic world of human experience, and when we carry them down into the quantum realm, they stretch and warp, and sometimes simply fail. We are, he suggested, like people who grew up on the surface of a calm lake and then dove for the first time into its depths and found that none of the navigational tools we had built for the surface apply in the deep water. New tools were needed, new words, new ways of holding reality in the mind. 100 years into the quantum revolution, we are still building those tools, still finding new words, still discovering that the deeper we go, the more the depths reveal. And here is something that should perhaps bring a quiet kind of comfort rather than unease. The fact that quantum mechanics is strange does not mean the universe is hostile to understanding. It means the universe is richer than we expected. Every paradox we have explored tonight, every superposition, every entanglement, every tunneling event, every vacuum fluctuation is something that was there all along, waiting to be found. Waiting for humanity to become curious enough, careful enough, precise enough to notice it. The universe has been doing quantum mechanics since the first second after the Big Bang. We have known about it for roughly a century. We are in some sense very new visitors to a very old reality. And the more we learn, the more we find that quantum mechanics does not just describe the strange behavior of electrons in laboratories. It describes the architecture of everything. The nuclear reactions that built the elements in stellar cores, the chemical bonds that assembled the first self-replicating molecules in some warm ancient ocean, the protein folding that may depend subtly on quantum coherence in ways biologists are still mapping, the photosynthesis happening in every leaf, on every tree, a process so efficient that researchers now believe quantum effects may play a role in how plants harvest light, guiding the energy of photons through molecular networks with a precision that classical physics alone cannot explain. In 2007, researchers at the University of California, Berkeley, published evidence that energy transfer in the photosynthetic complexes of green sulfur bacteria, showed quantum coherence, a kind of quantum wave-like behavior that allowed the energy to explore multiple pathways simultaneously and find the most efficient route. Life, it seemed, had discovered quantum mechanics long before physicists did, had been using it quietly for billions of years in the business of turning sunlight into existence. We are not separate from the quantum world. We are its ongoing experiment, its most recent and most self-aware expression. Have you ever stood outside on a clear night and looked up at the stars and felt, without quite being able to explain it, that you were somehow part of what you were looking at? Not separate from it, not just an observer of it, part of it. If so, you were closer to the truth than you may have realized. Every atom of carbon in your body was forged in a stellar core by quantum tunneling. Every photon that reaches your eye from those stars began as a quantum event, a probabilistic outcome, a wave function resolving into light. The universe is looking at itself through you. The strangeness and the wonder and the uncertainty are not outside you visiting. They are inside you constitutive. You are made of quantum laws. You are an expression of them, a temporary, improbable, extraordinarily complex arrangement of quantum fields, briefly coherent enough to be aware of itself. That is you. And it is breathtaking. Now here is a question to carry into sleep, not to answer tonight, but to let drift and settle and perhaps return to in some form over the days ahead. If the universe at its most fundamental level is probabilistic, if no outcome is determined in advance, if every quantum event is a fresh choice drawn from a distribution of possibilities, what does that mean for the story you are living? Not in a mystical sense, not as an escape from responsibility or consequence, but in the quieter, more personal sense of knowing that the future is genuinely physically, mathematically open, that the universe has not already written what comes next, that the wave function of tomorrow has not yet collapsed. There is freedom in that, a quantum freedom, small perhaps, hedged by circumstance and history and all the ways the macroscopic world constrains us, but real, grounded in the deepest physics we know. The universe holds its possibilities open until the last moment. Perhaps it is not unreasonable to do the same. Physicists Richard Feynman, who contributed as much as anyone to our understanding of quantum electrodynamics and the quantum vacuum, once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. He said it with a laugh. But underneath the humor was something genuine, a recognition that the theory works perfectly, predicts everything we can measure, describes the universe with extraordinary accuracy, and simultaneously defies every intuition we have built through a lifetime of living in a classical world. Understanding quantum mechanics in the deepest sense is not a destination. It is a direction. We are all perpetually in the process of understanding it a little more than we did before. Tonight together, we walk 9 doorways into that direction. We stood at the edge of what the universe revealed about itself when scientists were brave enough and patient enough and precise enough to ask it very small, very careful questions. And what it told them, what it tells us still, is that reality is not a fixed, definite, prearranged stage. It is a living, fluctuating, entangled probabilistic process. And we are not the audience. We are in some irreducible way participants. Thank you for drifting through this with me tonight. Thank you for letting the strangeness in, gently in the quiet hours, for being curious and patient and willing to sit with questions that do not resolve cleanly, the best kind of questions, the ones that keep the mind alive and wonder intact. The quantum world will still be there when you wake. The vacuum will still be seething. The entangled particles will still be correlated across space. The tunneling will still be happening inside the sun, inside the atoms of your body, inside the electrons moving through the chips of every device you own. Everything is still strange. Everything is still beautiful. And there is so much more to explore. The next story is already waiting another journey into the hidden structure of the universe. Another layer of reality that looks from the outside, like ordinary science, and turns out on closer examination to be something that quietly changes the way you see everything. Rest now. Let the quantum world do what it does best, hold all possibilities open softly in the dark. Sleep well, dream gently. Good night.